All right, so just really quickly, some of the stuff that I'll try to talk about today. I'll give a really brief introduction to the disaster health work that we're currently building at the Applied Physics Lab. I'll try to frame the problem space, at least as we're perceiving it. I'll talk about some global health security implications of pandemics. We'll put forward a solution that we think could provide some benefit to the field. Then we'll take you through a pandemic flu simulation that we did, I guess a couple months ago now, right? And then some challenges in future work. I did want to just start with a couple acknowledgements, specifically of Dr. Katz and Emily, because in large part the work, in particular the project that we put together and the simulation we did, came directly from motivation from discussions that we had or that Sherry Lewis, also at Applied Physics Lab, had with Dr. Katz. And then of course, as I mentioned, Emily had put in a lot of work in terms of looking at the sorts of available data that could potentially be used to do some of these kinds of simulations. Also, the Center for Health Security, part of this project focused on healthcare coalitions, and we leaned on a couple of their senior staff, Dr. Crystal Watson and Mr. Matt Watson, who provided us a lot of the subject matter expertise around healthcare coalitions. Okay, so our disaster health initiative, our mission is to enhance the United States government's engagement in disasters by providing health-enabling solutions and capabilities aimed at achieving a rapid, coordinated, and effective response. The way that we're thinking about this initiative at the current moment is that we have 4 focus areas. The first is advanced modeling and simulation for large-scale, complex regional disasters. So from an academic perspective, I came from the Hopkins Bloomberg before the Applied Physics Lab. And when we think about modeling and simulation, we can usually achieve breadth or depth, but it's really hard to do both. And that, to me, is a problem that I think is particularly right for some of the capabilities that are housed within the Applied Physics Lab. We are particularly interested in surveillance and rapid needs assessment. The project that we'll present today actually combines both modeling and simulation with rapid needs assessment. Detection and prevention of high consequence exposures, and this can be everything from toxic industrial, chemical, and material exposures of first responders, say following 9/11, to vector-borne exposures to malaria of soldiers setting up Ebola treatment clinics in West Africa, and really anything in between. And then the last area that we're putting a lot of attention to is what we call agile engineering for an adaptive medical response. And the example that we like to give is the idea of the military's mobile medical units, which are mobile but not quite adaptable. And so at a really high level, we might think about, how do we re-equip, re-engineer, or reposition, or restaff within the existing workflows the mobile medical units to make them more useful for a wider range of potential threats. But we could take that all the way down to the equipment level and think about reusable ventilators. I know there are folks that are already working on that. Detachable heads to stethoscopes was something that was called out in the after-action reports for Ebola. So, as I said, at a low or high level, I think there's a lot of work that can be done there. Okay, so looking more at the issue that I think is most relevant to this seminar and to the work that we'll present today, disasters are increasing, right? They're increasing in frequency, they're increasing in complexity and severity, and that's due to a wide range of factors, but I think there are a few that are particularly relevant here. The number and intensity of extreme weather events has all kinds of implications. The pace of urbanization is a major contributor. Shifts in warfare from traditional war to intrastate warfare has kind of shifted the theater of war from the battlefield to the neighborhood, which has all sorts of implications as it pertains to civilian populations, as it pertains to the availability of basic health and human services, which of course leads to all kinds of downstream effects such as outbreaks. I mean, you see this in large part in Syria, right? As the conflict has borne on, you see just kind of drastic drops in vaccination coverage. The rise of the global economy, markets, travel, and then increased threats from emerging infectious diseases. And that's really the one that we're focused on in this presentation. We think about disasters at the Applied Physics Lab as a big data problem, and I try to use that word sparingly because I know it's a buzzword, but I actually think by definition disasters are a big data problem. If you think about data volume, velocity, variety, and veracity, disasters have a massive amount of data. That data is coming in quickly, it's heterogeneous, it's structured, semi-structured, unstructured. It is changing as quickly as it's coming in, and understanding what's true versus not. It's how do you, for example, how do you differentiate between what is a true signal versus what is just an echo chamber, right? And that's something that I think is a big challenge. And pandemics are particularly data heavy. The branch that I used to work at CDC, one of the problems that they've put to us is this idea of dealing with the massive amount of data coming in the field that is kind of superimposed on the existing surveillance or data and information systems. You have a major event, you have a massive new amount of data coming in and data structures that are put in place, and how you actually leverage that, I think, can be a challenge. So how do you get effective disaster response, right? So you're going to need rapid, continual, event-dependent collection, analysis, and visualization of data. You're going to have to integrate and coordinate across disparate, often decentralized systems. And the hope is that in doing all of that, you can achieve real-time, operationally relevant situational awareness. And that sounds great, but it is a massive challenge and remains so. But we are in a different age, right? There are far more potential sources of data in disasters and really in all settings. And as a consequence, there's a greater need for interoperable and autonomous information systems. But sophisticated systems are only as good as their availability. And as you have more data sources, you have more targets and more vulnerabilities. In some cases, maybe that's nefarious. Maybe it's hacking the IoT of an ICU. But in other cases, it's just a matter of the field. I mean, if you've got more potential streams coming in, there's more opportunity for just basic failures in communication or information infrastructure simply not being available at a critical time that you need it. So I do want to call out some specific global health security implications as that pertains to pandemics, which is what we think about as a rolling disaster. Different from a point disaster like an earthquake or a hurricane. Pandemics, infectious disease events are rolling events, and they are, for a variety of reasons, much more challenging. Emerging infectious diseases in particular pose unique threats. Uncontained outbreaks, of course, rapidly proliferate. Pandemics require not just strong national responses, but also international coordination. And pandemics diminish the very same resources needed to contain them. And so what all that amounts to is kind of a window of response that you've got to hit, and you've got to hit well, because if you do not, you're going to see it get out of control. And so you've got to detect early enough, you've got to be able to respond effectively enough to contain it. And if you don't, you're going to see a lot of the effects that we saw, for example, in West Africa with Ebola. There are some challenges facing the United States. Pandemic threats to global health and economic stability are absolutely increasing. Land use change and urbanization is a major factor there, the global economy and travel. But technological proliferation, right? It's lowering the bar. What used to require a multi-billion-dollar lab or facility can now be done in a high school science lab. Now, it is true that this is still a technical challenge, right? But the idea that the challenges that remain are going to stay there, I think is a false concept. The remaining barriers absolutely will be removed, and so we have to prepare for that. And we also need to recognize that pandemics are fundamentally different from point disasters. They require a completely different response operation. If we look at the United States government and we think about their response to Ebola, maybe we call out some of the three big players. We've got the Office of Foreign Disaster Assistance, and because of, I think it's Presidential Directive 44, State Department, of course, runs the show, and that fell to OFDA. But OFDA is strong when it comes to point disasters, less so when it comes to rolling disasters. They don't necessarily have all of the subject matter expertise that they need. CDC absolutely has the subject matter expertise that's necessary, but they don't have anything in the total number of people or stuff that's necessary to respond. DoD has all of the people and stuff, but they take a supportive role, right? And they can't actually, it's not their primary job to respond to Ebola. It's not their primary job to respond to a disaster, and we have to recognize that. Their primary job is combat operations, and they have to maintain force readiness. So it's not by chance that they would drop CDC folk into the field, but then would not retrieve them, and they had to make their ways back. That actually is, there's probably a case to be made for why they could have retrieved them, but there's a very real concern within DoD that they have to protect and remain ready to do what it is they are actually tasked with doing. And so out of these three agencies alone, you have a lot of difficulty just in triangulating the U.S. government's response. Pandemic threats also, I think, and this is a really important point because I came from a humanitarian NGO that worked in war zones and was really strict on maintaining the principles of humanitarian neutrality and for a variety of reasons. But pandemics throw all that out the door, right? You no longer have the luxury of keeping that fine line there, if it ever was there fully, because you're going to require enhanced civilian and military engagement to respond effectively to a pandemic. And the bigger the threat, the bigger the need. And so this, to me, in large part, is a different kind of problem. There are some other key considerations. So if we think about this need for enhanced civil engagement on the domestic and international stage, we should also think about how both of those communities are shifting. From the civilian health system, which has traditionally been fairly disparate and decentralized, because of economic forces and others, the health system is beginning to consolidate, right? And so they're moving more towards a kind of closed loop. At the same time, DoD, which when you think about the way in which they used to engage in warfare, they could operate in a closed loop, but they can't do that anymore. That's not actually how most of their work is being done. A lot of it is now relying upon special operations, and so they're moving to what they would refer to as distributed operations. And so what you're seeing here is the civilian and health systems are starting to move towards each other. And they're converging in the way in which the challenges that they're dealing with. And so I think it's important to begin to think about if enhanced civ-mil engagement is necessary to have an effective response to pandemics, to improve global health security, then we might think about how the challenges that the civilian side has dealt with might be transferred to the military side, and how the technologies and the capabilities that the military is able to develop, how those might be transferred to the civilian side. And so that's in a little bit of the motivation for how we put this particular project in simulation together. So the specific problem we were dealing with is this idea that rapid needs assessments are often rendered obsolete, both by prior or false prior assumptions in planning and the rapid pace of changing conditions in the field. It doesn't matter how much you know. It doesn't matter how much experience you have. Half of your assumptions will be wrong. It's a fact. And that's not due to lack of preparation in many cases. It's just due to the nature of disaster response. And then, of course, the conditions on the field change. They're always changing. There are new players for the field. There are new dynamics that you're dealing with. And it's hard to predict. So our goal then, we wanted to design a semi-autonomous rapid needs assessment system that the U.S. government could use to enable real-time situational awareness during pandemic events. Our methods, we wanted to leverage a few existing APL-developed platforms for a proof of concept, specifically Essence, Dagger, and the EMCAP system, which I'll talk a little bit more about in just a second. But the principle here, in terms of thinking about bridging between civ-mil, is that we were leveraging what is ultimately DoD-supported, or at least funded technologies, with the ASPR-supported healthcare coalition as a model for response. Some of the system capabilities that we were focusing on, we wanted it to be able to do modeling and simulation for preparedness and planning. We wanted semi to full automation, immediate rapid needs assessment with minimal information required. If you knew nothing more than the starting point of an event and the event type, could you project forward all of the stress in your health system? And we wanted operationally relevant decision support. APL is, doing the work that we do, we are oftentimes measured not necessarily by what we can get funded or even the projects we deliver, but are those projects actually adopted? And if they're not, for us, that is sometimes seen as a failure. So we wanted to make sure we thought about the operational context. And our preliminary focus was pandemic events, although I think all disaster response might benefit from these sorts of capabilities. So some of the technologies we put to use here. Essence. So this is a syndromic surveillance system designed at APL that is both the DoD's syndromic surveillance system as well as CDC's national syndromic surveillance system. Some of you are probably familiar with it, and I won't belabor it too much, but this, as I said, this has been a flagship program for the lab, at least in the health space. Dagger. So this is something that has, up until this point, had never been used in the health space. We've used it in our space mission, our cybersecurity, as well as our special operations missions. It's a modeling and visualization tool suite that ultimately shows you how small failures can kind of cascade up a system and ultimately impact your mission status. A good example of how this works is how it's used with spacecraft. So when you think about the New Horizons mission that the Applied Physics Lab has that we sent to Pluto, and you think about that spacecraft right now, it is several billion miles away. And it takes 6.5 hours at current, or today, to send a message back to us. So whatever message we're getting in mission control at the lab is the past. It's 6 hours in the past. And whatever direction we send back, we're sending to the future. That's important because it means pretty much everything that we do with that spacecraft, we have to have anticipated before we ever send it out of the Earth's atmosphere, right? And that's a complex problem. So when you think about designing a spacecraft and you think about the redundancies that are necessary, you want to get that just right. Because any redundancy that you add is added cost, weight, complexity. It limits what the spacecraft can actually do and the value we can return from a scientific perspective over the long term. And so what this tool allows you to do is apply what's called failure modes and effects analysis, which allows you to look for kind of those single points of failure, allows you to think about how to get your redundancies just right, and allows you also to incorporate a probabilistic risk assessment and ultimately build the spacecraft that you need. When I saw that tool, I thought that might be a useful thing to model a healthcare response. Because in the same thing, if you think about disaster response, pandemic response, you're usually dealing with limited resources, right? It's an austere environment in another way. And so you want to get your redundancy right, and you want to get your scale right. And so we thought we could apply this kind of a model. The EMCAP system, this is something that was actually led by Johns Hopkins Medicine in terms of its development, and the Applied Physics Lab contributed to this. But it's just a model for plausible disaster scenarios. Simulates all kinds of data. You could do like dirty bomb explosions. You can do an anthrax attack. You can do pandemic flu, which is what we used in this case. So the system and simulation design, we used the EMCAP system for simulating the pandemic flu cases. We wanted something in the order of 1918 flu. We used Essence to feed our Dagger model with quote unquote near real time data. Essence, of course, is also used in the National Capital Region, and if you want greater fidelity, you can get data inside of 24 hours on what's happening in facilities across the region. And then we used Dagger to actually model a healthcare coalition for the DC area, and then also used it to measure the stress to health and medical resources in the National Capital Region. For anyone who's not familiar with the idea of a healthcare coalition, this is something that was in large part funded by under ASPR as a part of their health or hospital preparedness program. And it's basically, it was a degree of funding that was put to different geographic areas to get hospitals, doctors' offices, EMS, emergency response agencies, and the like to plan together, to coordinate, to share information, and hopefully have a more effective response when you have a major event, rather than trying to cobble that all together, after the fact. Okay, so our model itself, this is ultimately what Dagger looks like for a healthcare coalition. At that very top level, and I know it's a little bit hard to see, that's your most abstract level. That's your mission. And so in our case, our mission was to reduce excess morbidity and mortality. And we measured that by what we believed would be patients left untreated in a major event. If you go one layer below, that is a weighted average of your geospatial breakdown. So those are the 8 different wards within the DC area. You go one layer below that, and that's the weighted averages of the medical assets that we included in this model. So coalition hospitals, non-coalition hospitals, outpatient facilities. In this case, we use nursing homes because they can receive critical care patients if necessary. Federal medical stations, so alternate care sites. Federal medical stations are 250-bed staffed facilities that can be set up in anticipation of or in the middle of a major event. There's also alternate care sites that can be stood up within coalitions. In this case, we used one, which was like a 50-bed unit. You go a layer below that, and you actually start to have, instead of weighted averages, you have the actual status of individual inputs. So your federal medical station, your alternate medical station, your hospitals, your EMS, and the like. And the colorations represent status in the sense that green means a particular asset is operating at under its capacity. Yellow means it's going into its surge capacity. Red means it's beyond its surge capacity. It cannot manage the demand that's placed on it. And there's actually more granular detail that's not shown in this model, but we break those units then down into people and stuff, into trauma and supportive care, because we also ran some simulations on like mass casualty events and the like. You don't see all of that here just because it gets a little busy on a slide, but we could actually, if you wanted to, you can go as complex as you want, as detailed as you want. You could take it all the way down to the number of ventilators in a facility if you wanted to. Now, are you likely to get that information in the middle of a disaster? Probably not. But for preparedness and planning's sake and gaming it out, it's potentially useful. You can drill in on any of these parts. What you're seeing on the left is if you drilled in on your highest level, your mission status, that shows you all of the inputs coming into that. Areas that you see gray, that's telling you those are unknowns. You simply don't have any information coming in from that particular unit. If you look at a hospital, as what you're seeing on the right, you see its inputs coming in and the various statuses that are impacting it. This is just the visual aspect. You can actually look at the indicators. You can look at the data. You can look at this in a lot of different ways, not just coloration. So, for example, here you can see like baseline capacity in the hospital, overall capacity, surge capacity, number of cases in and out, and any other indicators that you wanted to include. We also added a geospatial aspect to this, where you can see in real time the status of your overall model. And again, that's kind of what you're seeing there for the DC area. So some model assumptions. These are based on best practices and subject matter input from within APL as well as the Center for Health Security. I won't belabor all of the assumptions because for us this is really just proof of concept, but some that are applied here. Federal assets require 3 days to become operational, so you can build them into the model, but once they're called for, we make the assumption that they're not actually available and running for at least 72 hours until they've been requested. We assume that coalition nursing homes could receive patients during a disaster. We assume that emergency operations centers, command and control, ultimately are what's enabling your higher surge capacity within the NCR's coalition. Yeah.
When you mean that coalition nursing homes can receive patients, does that mean that they're being shifted to a different use?
Yes.
Okay.
Yeah. Just saying that if required, they could actually receive some individuals that are maybe flu patients, or if it was a mass casualty event, they could actually receive care. Hospital stays, the EMCAP system was fine for simulating the data in, but we needed to deal with the data out, and so we needed to accommodate this. And so this was just an assumption used in terms of the average flu patient for a hospitalized patient is usually about 5 days. I do want to stress that this simulation was for proof of concept only. The model assets, so when we think about the number of hospitals and nursing homes and EMS units, They resemble the DC area in number, type, and capacities only. We did not put them in their actual locations because we didn't want to freak anybody out for like, why are you saying our hospital will be overrun? We didn't want to cause any alarm. But we did want to give at least a close approximation of what it might do to the overall DC area. Okay, so really quickly, I'll take you guys through the simulation. Okay, so on day one, a surge in the number of patients presenting with flu-like symptoms has been reported in the DC area. Both an increased patient load and higher than expected case fatality rate were first detected by the disease surveillance system for the National Capital Region, Essence. And that's kind of those are the dashboards you might see in the system. The severity of patient symptoms, many requiring emergency respiratory support, has caused strain on EMS throughout the DC area and led to an investigation by the Centers for Disease Control, which confirmed the presence of IJ1, a particularly virulent strain of flu circulating across the National Capital Region. In response to the DC Department of Health has activated their EOC and requested federal support in anticipation of a potential pandemic. And again, the colorations, although again it's kind of hard to see on the screen, but that yellow is essentially your EMS assets. And then you can see there is one hospital that has already moved into surge. Day 7. Patients presenting with severe flu-like symptoms to medical facilities throughout DC are beginning to stress the health system. Federal medical assets have been in place now for several days, but have not yet been required to meet growing patient demand. Most of the stress in the health system is being felt by non-coalition hospitals, which are having a difficult time increasing their surge capacities compared with coalition facilities, which are operationally linked to the EOC in the DC Department of Health. All right, day 9.
I'm sorry to ask all sorts of...
No, of course.
I should know this, but I don't. What percentage of the healthcare facilities in DC are not part of coalition?
Okay, so for that, I don't know with certainty, but we used about 15% of them.
That's
like in terms of,
part.
Not being a part.
So those
but
are the federal health center or something?
Yeah, and again, so we used, for this particular simulation, we used mostly major hospitals and then outpatient facilities, but we did by no stretch of the imagination included all medical assets within that area. So, in part for reasons of expediency. We did this on internal funding, so we tried to be efficient. Despite a heavy federal presence, including a contingent of infectious disease experts from CDC, the outbreak has not been contained. Hospitals are continuing to struggle to keep pace with increasing patient demand. Most coalition hospitals have been able to coordinate resources to surge their capacities to meet current patient demands. However, nearly all non-coalition hospitals have been unable to meet demand with their limited surge capacities. Federal medical stations are now receiving a steady flow of overflow patients from hospitals throughout the DC area. All right, day 13. Non-coalition medical facilities have now been completely overrun, forcing all new patients in their catchment areas to be sent to federal medical stations. Coalition facilities have continued to coordinate resources and patient loads with the Department of Health, but remain just under maximum surge capacities. Cases are now being reported in Baltimore and Philadelphia as health officials begin to worry a pandemic has emerged. So this next one is something we wanted to game with. Okay, so we knocked out the EOC. Now, this doesn't mean that this is actually what the effect would be, but our assumption was that coalition hospitals had higher surge because they were linked to the EOC and could shift resources around. Well, that's a single point of failure. And so if you were just playing with this tool and you knock out, that's that little red thing on the bottom there, you knock out EOC, you lose your assumption, and now they start to resemble non-coalition hospitals, and it basically blows up your system. Now, I suspect there would likely be other things done to accommodate that, but it's important to know, particularly in preparedness and planning, where your single points of failures are. So as it says, unexpected technical glitch causes command and control within the DC Department of Health EOC to go down. As patient demand continues to grow, and in the absence of a unified communication system, coalition facilities struggle to juggle resources and patients, leading to severe strain across the health system. Day 16, it's back online, and a lot of that stress is relieved. Technical issues have been resolved, and the EOC command and control is back online, relieving some of the stress across the health system, but cases continue to grow. The D.C. Department of Health has requested additional federal assets. However, the cases being reported throughout the Northeast Corridor, governors from Maryland, Pennsylvania, New York, Rhode Island, and Massachusetts have all appealed for support, leaving the federal government unable to respond to all requests. And at the next point, we projected forward to how many days would it take to truly break the system. And it was 36. So a full-blown flu pandemic is no longer just a concern, it is a reality. With federal assets deployed throughout the Northeast Corridor, no additional medical assets are available to mount a more effective response. The D.C. medical system has been completely overrun, and patients are being turned away from hospitals, outpatient facilities, and federal medical stations alike. Fearing the pandemic might reach their own states, governors across the U.S. have declared a state of emergency, mobilizing their National Guard, and are refusing to send additional medical personnel to the Northeast region. Okay. So some remaining challenges that I think are particularly important to this kind of a project. So models are only as good as their assumptions, right? And as I said, I readily admit, a lot of the assumptions we made are unlikely to hold. Going back to that point I made at the very beginning, half of our assumptions are probably going to be wrong. When we think about the way in which our national disaster medical system is designed, it operates under this assumption that if you're saying dealing with a point disaster and you lose power, you should be able to bring that back online inside of 3 days, 7 days max. As you can see from Puerto Rico, that definitely was not true. Right? And that has serious implications in terms of how we position resources and how we comport ourselves for response. What about surge capacity? We assume that coalition hospitals can surge to 20%. And maybe that's true for some hospitals if you're dealing with a mass casualty event, right? Because you're really shifting resources around to a large extent. But if all of your hospitals have to surge at the same time, do you really have 20% surge across the board? Probably not. And so what I think is critical here is that we don't just need systems or simulations or models that are dynamic themselves. We need dynamic assumptions. And so this is where I think you can apply deep learning and other machine learning algorithms to create dynamic assumptions that can detect when your assumptions are violated. They can correct those assumptions and, most importantly, modify the decision support that's tied to them. So, for example, if your system, your Dagger system for the National Capital Region says that if Hospital A is overrun, then you need to take patient overflow to Hospital B, to C, to D. But in fact, B has no power, or B is overrun because patients are going there for some reasons that were unexpected. Well, now you need to reroute to C, to D, to E, right? And you want your decision support to be live and dynamic. That's something that's hard to do in the middle of a theater, but it's actually not that hard to automate. And I think there are ways to do that. Bless you. So real-time situational awareness, if that's our goal, it requires real-time data. And everybody in this room, I'm sure, knows that is really, really hard to get. From a domestic standpoint, we focused on the NCR Essence, mainly because we knew we could get to near real-time data for some of that stuff. We also wanted to focus on healthcare coalitions because we think that they're a wonderful foundation, at least domestically speaking, to kind of build off of to get some of the data that's critical in the middle of an event. But the indicators that we're even thinking about pulling in are probably not sufficient, right? A lot of our model that we built was based on this idea of bed capacity. But bed capacity is not actually the most useful indicator, right? If you think about Las Vegas and the major hospital that received a lot of the patients after the shooting, if you'd asked how many critical care wounded folks you could receive, they probably would have said 10 to 15, and yet they received well over 100, and they did just fine, right? So that's not a truly meaningful indicator. It doesn't mean it's a useful one, but it means it's maybe not the most meaningful one. And so we need to think about non-traditional data. How do we get real-time data? So video recognition, right? If you have video eyes on an emergency department, which we do throughout the entire National Capital Region, you know if that facility has hospital or has power. You know if that facility is still receiving patients of people coming in and out. And we have video recognition algorithms that can absolutely do that. Satellite data, if we're talking about damage, infrastructure, transport, a lot of the work that we do, is particularly in our space mission, is to put together a lot of the information infrastructure necessary to derive meaning from satellite information and do it in real time, right, to gain access to the national assets and derive meaningful information from them. But also minimum data requirements. So one of the uses of this tool that we thought might be useful is you take and you make your really sophisticated granular model of your environment, in this case the NCR and its health and medical response assets. You then duplicate that model, and then you start pulling stuff away from your duplicate model. So you pull data you expect you're never going to get. As I said, the kind of more granular stuff. Start pulling it away, pulling it out, piece by piece. See when the colorations change, but more importantly, when does your decision support become nonsensical? Right? And at that point, you can kind of know that here's the absolute minimum data requirements that are necessary to be informative. Now you can look at those minimum requirements and start to say, yeah, we're likely to get that. We are not likely to get this. And now you can start thinking about, all right, well, these are the data points that we have to find alternatives to. And you can start to think creatively about that. But there's also no existing business model for preparedness and planning, particularly from the domestic side. It's why you have to incentivize with dollars hospitals. If not for the money that the Hospital Preparedness Program through ASPR gave to these facilities, it is unlikely that healthcare coalitions would exist at all. And so we need to think about how we achieve a viable business model. And this absolutely applies in a global health context as well. There's a lot of talk about using drones in humanitarian settings. But I mean, there was actually, I was in Madagascar doing some TB work, and there was like one group that was talking about a $20,000 drone to transport medical supplies. Well, one, how are you repairing that drone? Do you have engineers that are capable of doing that with that sort of technical sophistication? Do you have supplies? Not in Madagascar, right? Like, and if it crashes, $20,000. I mean, so, or if you think about off-grid solar in sub-Saharan Africa, if there's not a business model, these things cannot survive. So we have to think about that at the very beginning stages. Now, if we pull it back to the domestic side and we think about hospitals, well, how might this sort of thing be useful to them? Well, the Dagger model might actually be quite useful for health systems optimization, for looking at supply chain monitoring and optimization within a hospital. It's something that you've got to give it a day job. If you cannot give your capability a day job, the likelihood that it will be used in a disaster or scaled when critically needed is minimal. And so we have to think about that early on. And I think that there are absolutely doable solutions for that. There are more challenges, but I wanted to make sure I did not go on too long and that there were time for questions.
Can I ask you a real quick question? Probably way more granular than what the conversation should be. Mm-hmm. But does the data that Freeman also include staffing? So say you say you have eyes on the emergency departments, but does it have a way to assess how many people have called in sick that day? Mm-hmm. Because I know the issue isn't necessarily the beds, but it is the staff. Right.
Yeah. So our model assumed you were feeding in that data. In fact, you can pull out staff if you want to see what the impact on a particular hospital, and you could take it down to the individual type of staff. But that's all notional, right? Like these hospitals are not necessarily providing that in the middle of an event. It's one of the reasons why, going back to the day job or use case, is if you actually are implementing Dagger within a hospital system, within an EHRS or something like that, to actually monitor to get to your optimal staffing needs, well, now you actually have those data points in real time. In which case, if you needed to turn that spigot on and feed an integrated model within, say, ASPR's EOC, you in theory could do that. But we have to figure out a way to actually get hospitals to share that information, and I think that remains a huge challenge.
Follow up. Does that mean you essentially need to be linked into their operational systems so that they don't have to make any extra effort to feed in information and data?
I would say optimally, yes, we would love to put Dagger as an optimization tool for hospitals as a part of a coalition into their facilities, but walled off, right? But integratable when necessary. Because everybody wants to share when you're in the middle of a horrible event. Yeah. Nobody wants to share before then. And so if we can give them that day job, then we think, okay, major event, now let's turn that on. But yeah, we think it would need to be integrated within them.
And that's going to be tricky.
Absolutely. Absolutely. Yeah, we are I don't want to oversell what the solution could be, because for the reasons you are well aware, are our big challenge. Jamie?
Thanks for your very interesting talk. A couple of very different kinds of questions. One of them is, so this is an interesting model. Wondering if you could use this to model the upper limit of what sort of regional healthcare systems can tolerate. Because my impression is that once you get to a certain order of magnitude of cases, the whole system is going to collapse. But we don't know what that order of magnitude is, or maybe we do. But it'd be interesting to know if this, like, how much confidence this model could sort of start to estimate the order of magnitude where things break. And then also, if you could figure out the critical investments that are going to have the most marginal impact on increasing surge capacity and stretching the limit based on what we have, that would be really interesting. And then because I'm always thinking about the sort of deliberate attack side of things, hearing about EOC being a single point of failure that turns the whole field red is really scary to me, for obvious reasons. And it seems like if you're trying to do deliberate attack and have cyber capabilities, why not release something and also hit the EOCs, right? That's really scary.
I am certain those things will eventually be paired together. That's why I mentioned that cybersecurity risk, because we are more and more going to lean on these kinds of systems. So
the question there is, how resilient is the EOC? How realistic is it that we could transfer EOC unified command structures to a redundant system? I mean, is that something where it's like, oh crap, we are not ready, we need to build that, or like we've got that, we're ready, this is going to be achievable in a few days? Because I think it's a really important thing to know.
Well, I mean, even just taking TC as an example, so in this you're standing up the Department of Health EOC, which is that switch to HCMA's district-wide Emergency Operations Center. And at what point does any event transfer at that? And it's the same on a global scale. At what point are we beyond Ministry of Health?
Yeah, I know. I mean, I work with the committees of the COG, so I know that they have some redundancies that they work and they exercise. And I think we could definitely add that into the sort of the model and say there's this capability that exists. So there are EOCs that, the whole model is built so you can move it around, right? The whole unified command model is built so you can move around. So there is some opportunity there, but to the extent that they can work in practice, you know what I mean?
Yeah, I mean, I think.
Yeah.
So
should that be drilled? I mean, should be practicing that?
Yeah, and I don't want to, there's a lot of stuff on the back end that when we designed this, we were just not privy to, right? That redundancies that may or may not be there. To do this truly, you would actually want to work directly with the coalition, directly with ASPR, as well as the DC Department of Health and others. And then it can more closely resemble that. To the question of the critical needs and what that does. One of the best uses of Dagger in general, and just in how it's been applied, is but a lot of the value is actually building the model with the people. Because what you see what you don't know, and they learn what they don't know, because the model will show you that. It grays out what's lost, what's not there. You can then start to play with it a lot to see, is it even a sensical change? Like if you lose this, one of the things we were interested in was using this for medical supply chain across the U.S. just to map, because it has a geospatial aspect. Let's map all of the industry that feeds and stuff. What are the critical supplies for different types of events in hospitals, and where are they coming from? So if you were to say have an earthquake in this area, a hurricane in this particular area, what is going to be the downstream effect in terms of medical supply chain, and that could tell the U.S. a lot in terms of we need more redundancy for, say, saline solution, right? For example, So yeah, I think there's a lot that can be done there, but I think one of the essential points here is that we need to go into this knowing that, as I said, half of what we're assuming will be wrong, and so we want to build models and systems that do change in real time, that detects, in fact, things are not going how we thought they would and can simply correct itself. We absolutely have the CS capabilities right now to do things like that. It's just that in large part, for a variety of, probably a lot of the same reasons for getting access within those hospitals are, the health system is not as sophisticated as many other environments. And so figuring out how to actually move towards a more technological ecosystem while also avoiding the obvious threats that moving, ship. Again, I mentioned the IoT in an ICU for a reason. That sounds great, but you hack an IoT of an ICU and you kill people. I mean, there are so many different, I shouldn't be smiling talking about crazy challenges like that, but it's an interesting problem.
I just had a data question about some of these things, call-out rates during an epidemic. Is it possible historically to get some sort of average, a big event? What was the call-out rate of hospitals? How many is that work showing up? Is that historically exist? So you can make a more informed assumption about what that's going to look like if you do that in, say, maybe it's 7% or whatever percent it is. Does that data exist, or did you know?
There is literature on that. We did not include that as one of our assumptions, just because we were using, pandemic flu. So.
I mean, there's been some interesting stuff in New York City on that question, but I don't know if there's been a similar.
It'd be hard to extrapolate that into something.
It might be. I mean, you have to check it.
The current HHS plan, I think, says 40% loss of staff due to falling in sick, as an assumption, which means, could be 50% chance that's entirely wrong.
But you at least have some sort of.
It's not as good as we need it to be.
Yeah.
I'm going to ask you to go a little bit outside the United States because you mentioned that you had been to Madagascar. Mm-hmm. And I wonder if, two things. One is, if you could describe the process of trying to apply this in a resource-constrained environment. Yeah. And secondly, whether you're going to produce a lessons learned document that might be looked at by others across the country.
Yeah, so I can say one of the interests of this particular method came from UNOCHA, who wanted to apply this to model the cluster system. So I come from a global health background. The group that I work for was a group called Emergency that provides medical surgical care to the civilian victims of war. At least previously, before I was at CDC. And then, of course, CDC's Emergency Response and Recovery Branch works entirely in those settings. But I think it is always a challenge to apply any sort of technology in a particularly austere environment. I think what is often the case is we have a technology and we try to superimpose that onto a use case, which, of course, is exactly the opposite way that we should do it. Rather, we need to define what the parameters are of a particular environment and then build your technology to meet those parameters. If it's a drone, if you really want to transport medical supplies on a drone, well, you need to think about the engineering capabilities, you need to think about the cost that needs to, all of the parameters that need to be met, the fidelity, the travel time, etc., in order to apply it in a very, in a way that makes sense for that environment. This particular methodology, I think, is doable, but challenged in, say, in Antananarivo or Ifanadine, in that, well, in Ifanadine would be a little bit easier because you know the players. In Antananarivo, you know the key players, but you don't have access to everything you need, and you don't actually know what all will be there in the event of a major event. So in the U.S., you can kind of predict if you have a major event, the U.S. is going to position a massive amount of supplies to the perimeter of disaster, and they're just going to move stuff in as you need it. Not in Puerto Rico, because it's a lot harder to do that, right? But in an international context, so much of the supplies, say with plague in Madagascar, Ebola in West Africa, are going to come from the international community. And so you have this entire ecosystem that's superimposed onto an existing country. And it's really hard to predict that. And so how you model something like that when you don't actually know what the international community on any given year will actually deliver to the field, I think is probably the primary limitation to deploying this kind of a thing in that setting. It's still doable, but you would have to limit it to the key players that you know and the pieces that are put together in that way.
But you can maybe use these tools to make better decisions.
Absolutely.
And actually professionalize the response.
Absolutely.
Right. So if you actually had an accurate account of what the indigenous capacity was, mm-hmm. and could actually identify the geographic regions within people's.
Yeah, absolutely agree.
Preposition, you can move things around, you can, maybe the cluster would be less of a cluster.
Yeah.
But again, all of this is, it's data in, data out, right? So if you don't have the data to put into it.
Yeah, I think for preparedness and planning, it's solid, right? Like you can spend the time, you can do that stuff. It's once you're in event, the degree of achieving that real-time situational awareness, I think that's where those limitations really start to be imposed. It's not that I'm saying there aren't solutions. I think there absolutely are solutions for that, but getting to those minimum data requirements and making sure we have the appropriate redundancies in place to get that information at that critical times, I think, is where we have to move.
Sorry to follow up, but also the process. The question is, did you only meet with technical people in the Ministry of Health or their National Preparedness Committee, which might include environment, agriculture, and the whole zoonotic story, or was it essentially drilled down into the people who may not be as technically familiar with this kind of issue? So the process is something.
Yeah, so in the case of Madagascar, so again, that's kind of an unrelated, it was for tuberculosis, but absolutely we were with the ministry. We were with Institute Pasteur as well, which has a major lab in Antananarivo, the capital. We were with a group called Pivot that really does a lot of health systems work. And then, of course, at the community level. And so we went into that. We allowed that country, those communities we were looking at we allowed them to define what we ultimately delivered. We originally were looking at the project that we did. We were interested in like minimally invasive. We were actually dried blood spots, right? Like was a thing we were trying to put in the field, how in the absence of cold chain, et cetera, et cetera. But we wanted to do it for like some sort of exposure that I won't say now that they didn't care anything about. And like, actually what we care about is tuberculosis, right? Like how can you pair? So then we reached out to Stanford. They had a particular approach to TB that was promising. We paired with them. We looped in all kinds of other people. It's actually an interesting project in and of itself, because as we kind of went through the paces, it was like we run into a problem and then we just bring in a new collaborator. They would solve that, and then we'd hit the next problem and we'd bring in the next collaborator. When we wanted to field test our stuff, we didn't have a rainforest to field test, so we pulled in the National Aquarium in Baltimore and used their rainforest exhibit, like whatever it was. we just kept bringing stuff in. But I will say that where we really benefited from was Pivot, just this small NGO, because they were so integrated within the community. They had the ground game in place, and they made all of the work that we needed to do possible and useful. Anytime we needed collaboration or cooperation at that ground level, they could bring that in, and they helped us avoid a lot of the mistakes that I can say, looking back now on the original plan, I was certain to make those mistakes if not for them. So it was really great in that way.
It's an interesting point about the need to simulate more, though. And the EOCs, if nothing more, even the biggest EOCs, to do simulations to at least see where your data holes are. I mean, because the only way to test this and see what you're going to get is as you did in Madagascar, get as close to real world as you can.
Yeah.
I wish there was more of an appetite to fund those through cities and other places, because the EOCs, again, the weakest can still simulate. And I think that's where you have to do it. And if we could get more of that going on, this would work, and you could see what sort of notes and points of information you have. Yeah. If you say Pivot, probably would have never put on a model until you went to Madagascar and said, hey, this is this great localized thing. So stimulation aspects is something really big, but no one seems to simulate this in real season.
Well, I mean, there's real questions around the utility of models and simulations in general. I actually had, while working on a model, I had a professor at Bloomberg tell me, modeling is the lowest form of science. Which, like, could have been said more like modeling has challenges, So I think that there is real skepticism around the utility. And that's why we always have to think about, okay, here's the model, but what's the operational relevance? How do we actually make it useful? And how do we prove it was useful? And all of that has to be pulled in at the very beginning, because if we're not doing that and we're not demonstrating that, we know there's not going to be an appetite. I can tell you that the folks that we've talked with at CDC absolutely do have an interest in that sort of thing, but they are also cautious, and they want to make sure that if we do something together with them, that we don't miss. Because if we do miss, then we give the ammo to people like that professor to just be like, yeah, there's no value here. And obviously, I agree with you, there is value.
Yeah, just to pick up on that thread, I mean, I think people like to poo-poo models, but I mean, honestly, the alternative is human intuition, and human intuition is like deeply flawed.
Absolutely.
And it's not transparent, right? It's in someone's head, and they say, oh, well, I think X, Y, Z. Okay, well, that's great. That's your intuition. How do we unpack that?
Yeah.
This model lets you see what the assumptions are.
Yeah.
And the other thing I wanted to ask was, obviously we made a lot of assumptions here that are not as close to the real data as you would like, but I'm wondering if you've done a sensitivity analysis to see, okay, how sensitive are your answers to assumptions you've made, right? So if you do a sensitivity analysis and you say, oh, well, I changed these 10 key parameters by an order of magnitude, and either changes everything, like flips it on its head, or doesn't make much of a difference, that tells you that you're converging, you're pretty robust to the assumptions. And so I think, have you done that?
In this case, no.
Okay.
No, we wrapped it on the simulation and stopped there. But it's certainly something we have interest in, would like to do. I also want to just say on the point you made, I think that's a really great point regarding the alternative. And I think oftentimes, particularly when you talk about technologies or moving the ball forward a little bit, the world is full of people that will tell you all the reasons why something can't work and very rarely tell you maybe how it could. And the same thing applies to anything, is that we need to stop comparing whatever we're proposing to perfect, because it's not a real thing. What is the actual alternative? And if the actual alternative is worse, if the status quo is worse, well, let's take slightly better. And slightly better to me is a win.
It's just talking about the assumptions that have been built into the model. Some of the models, well, a lot of the models that are out there are very focused on, getting as close to the real data as you can.
Yeah.
I would be interested to see some more assumptions around the actual process around all of this. So building in assumptions for example, the situation about privacy. What is the time delay in terms of, okay, so this hospital is a private entity, they're very protective about their data. How long will it take them to, release anything, no matter if they have the real data or not?
Yeah.
That process, I think some of the models lack that part. And in many ways can be that, it's not a single point failure, but it can cause a lot of those failures, even if you have the real data, because exactly what you need.
That's a really great point. Yeah.
And that's just one example, but I think there are several assumptions like that could potentially make those models stronger. But we're looking at the technical data when we should be looking contextually around what allows that technical data to get into place. Whether that's the actual staffer sitting there plotting in this data. I know with real-time case surveillance data for example, HIV, which I worked a little bit with, it's just, even there, it's.
Now APL is hiring, so No, I really appreciate that. That's a great point.
And in fact, InQtel,
sorry.
two fingers, I'll be really quick. InQtel is looking a lot at biosurveillance and the data wrangling problems, not so much about the response side, but the detection side. Yeah. And I think a huge point that they're highlighting is sort of the fragmentation of data and the difficulty of getting people to share data quickly. So I think that's very real, and it's going to be a major problem in our crisis.
Absolutely.
Nathan and Emily, and then we're going to have to wrap.
Okay. So I'm interested if you thought about any deliberate biological scenarios.
We did.
Any work on that?
So just for
the difficulties of well, what if 40% call in sick? Well, what if all the resources dry up and no one bothers to report any of this data anyway? Just wondering if you've looked at that.
So we didn't in any of the scenarios we didn't actually gain too much with people and stuff. But I can tell you the scenarios that we ran on this were pandemic flu, a anthrax attack, an intentional bubonic plague attack, a coordinated attack on the DC Metro culminating with a dirty bomb at Union Square. Is that all of them? It sounds like them. Yeah. So those are at least the ones that we ran.
I'm going to give you my card later. Yeah.
So when you were talking about the situation in Madagascar and TPD and using the cooperation with pivot. In a situation where you don't have someone you're easily able to cooperate with, how do you accommodate the institutions or players like pivot or at the level of pivot that don't cooperate in a model?
So I should be totally clear on that. The Madagascar work was not modeling work. That was actual tuberculosis. Like, we were delivering capabilities to enhance TB surveillance in the field. So we developed methodologies for collection. So anyone, anywhere, anytime could collect. We paired with Stanford to provide a diagnostic that could actually that could have better sensitivity and specificity, that could differentiate between latent versus active, that could predict when latent would go active. So that was not a modeling experiment. That was actual materials science capabilities where we were trying to stand up a biosample referral program for the country. What I can say, but having said that, when you talk about the lack of participation, you need to be really clear, particularly on modeling, that that's a blind spot, right? I mean, you can make assumptions, but as I said, your assumptions are likely going to be wrong. And if you are lacking participation from those key players, you've got to be really clear on the fact that your model, your system, whatever it is flawed and is majorly flawed. Right? Because even if you have full cooperation, you're still going to get a lot wrong. But if you don't have key cooperation from those players, you should really take a step back and question, should we be doing this in this context at all if we are not at least including the major stakeholders? So it's not to say there's not a reason to do it. As I said, if you can move the ball a little bit forward, maybe do that. But you really have got to be open with the limitations in what you're doing. I mean, and that's a really great point. And sometimes you just don't get that support. A lot of the work that I did in Haiti in terms of maternal and child health, we didn't necessarily have the cooperation of all the people that we perhaps really would have liked to have. And that, in and of itself, was a big limitation. That's a really great point.
So I think we have to wrap, but hopefully Jeff can stick around for a few minutes and ask some other folks who have additional questions. But if you don't join me in thanking Jeff and the rest of his APL colleagues for being here and for sharing this with us. This has really been an interesting morning. I'd also, just as a quick plug, next Friday at 9 a.m., as opposed to our normal 8 a.m., Nancy Knight from CDC will be here. So she'll be doing the seminar next week. And then on April 20th, Tim Ziemer from National Security Council will be here back at the 8 a.m. time. And all in this room, and that'll be our wrap for the semester, and then we go on academic schedules and take the summer off. So
I do just want to make I just want to reiterate one more point. None of this work would we have done if not for Dr. Katz. So let me just be totally clear on that. So thank you actually, because this was it came, as I said, it came directly out of conversations you had with Sherry, and we had a lot of fun. Doing it. So thank you. Thank you.
It should be fun.
And thanks for having us.
Thanks to Emily, too, for all the work she did over the summer and kind of digging knee-deep in a lot of data.
Which is hard.
So thank you. Thanks for being here.